Hello everyone, welcome to the Material Science class, Make 300. This is the second video for Chapter 4. In Chapter 4, we are discussing the imperfections in solids. We said that the real crystal structure or the real material structure contains some defects and different forms of defects, and the material properties somehow are related to these defects. We said that it is impossible, kind of impossible. It is very hard to find that ideal material that we were discussing in Chapter 3, but instead we're going to have some imperfections and defects that would be located inside the material structure, whatever at the atomic scale or the microstructure scale. And the objective of Chapter 4, as I mentioned, is just to discuss these different types of defects and imperfections in solids. So we said that in general, we do have three groups of defects. We do have point defects, which are related to points or atoms that they are not located in their position, or missing atoms, like the vacancy atoms, interstitial atoms, or substitution atoms. And this is what we covered over the last video. Also, we have line defects and planar defects. So this is the second video of Chapter 4, and we're going to continue discussing these different types of defects inside the material structure. Alright, so over the last video, we discussed alloys or alloying. Alloying is a method or a process of adding impurities into the pure metal to end up with a good material. We said that metals are barely found as 100% pure metal, or even the 100% pure metal. It is a very weak material and it is not preferred from the engineering perspective or engineering applications. So that's why we intentionally adding impurities in the form of non-metals to enhance, with the purpose or the objective of enhancing the properties of this pure metal. So we're going to end up with an alloy, as we discussed, and this should be done over some chemical reactions between this metal and non-metal elements. So it is a chemical compound that is formed between metal and non-metal elements. But the key condition is, as we discussed over the last video, is that the percent or the fraction of the metal, it should be higher, much higher than the fraction of the non-metal. The non-metal, it is very small concentration, or is very small fraction inside the material structure. And depending on the fraction of these non-metals and how many non-metal elements that would be used for making this alloy, we are ending up with different material properties. Like, for example, if you have aluminum, and you're just gonna add cobalt to it, or add another element like iron, or add any other element as non-metal elements like carbon or any other non-metal element, you're gonna end up with different mechanical properties and chemical properties and thermal properties of the new material. So the new alloy, its properties mainly depend on the concentration of the different elements that form this alloy. This alloy could be made of only one element, or it could be made of multiple elements. So we discussed that these alloying things, and we discussed this as a one type of the defects that would be located inside the material structure, and we are intentionally doing this thing to achieve good properties to this pure metal material. So as long as everything is related to the concentration or the composition or the percent of these metal and non-metal elements, especially the non-metal elements inside the material, and all the properties are related to these percent. So it is highly important to know how we can calculate or estimate the composition or the concentration of the different elements that would form any alloy. And this is the first thing that we are going to start in today's video. Okay, so there are two ways in estimating the concentration or the composition or the fraction or the percent of one element that form an alloy of the constituents in a solid solution. As we discussed the last video, we said that the alloy could result in a solid solution, and this is what is likely to happen in many of the cases, but in some special cases we would end up with a new phase. And we distinguish, or we said that what distinguish a solid solution from a new phase is that the crystal structure, it is maintained or is going to change. If the crystal structure is going to change, it means that we're gonna end up with a new phase. But the solid solution, it means that there is no change in the original crystal structure of the metal material by the addition of the non-metal. So the non-metal, it is a very small fraction of the material, which in many cases will not change the crystal structure of the material. So that's why we are going to end up with a solid solution as long as we are interested in alloying. So the question is, if you do have an alloy like this one, assume, for example, that it is made of two elements. It could be made of 2 elements, 3 elements, any number of elements. It doesn't matter. One of these elements definitely should be metal. The other element should be non-metal. As I mentioned, we could add any other more elements, whatever metal or non-metal, to enhance the properties of this material. In many of the cases, they're gonna be non-metals. Make sense? To end up with an alloy. So let us assume the simplest form of this alloy, that this alloy is made of two elements only. And the question is, what is the percent? What is the concentration or the composition of element 1 within this alloy? Element 2 within this alloy. So this composition, it could be calculated either as a weight percent or atom percent. What is the weight percent or atom percent? We just gonna identify the fraction of this element within this this material structure or alloy structure based on the weights or the masses of these different elements, or based on the number of atoms that belong to this element and this element. So the percent weight is the weight of a certain element, the weight or the mass of a certain element relative to the entire weight or the whole weight of the whole alloy. Like as I mentioned, if we assume that we would have an alloy of two elements, so M1, this stands for the mass of element 1, M2, this stands for the mass of element 2. So if we are interested in the concentration or the composition of element 1, it will be the mass of element 1 divided by the total mass of this alloy. So in the denominator all the time we are adding or putting the total mass of the alloy, which we are assuming that it is made of two elements, so that's why we are summing M1 and plus M2. If we have three elements, so we should have plus M3. If we have four elements, plus M4, and so on. So the key condition is that in the denominator we should add here, or we should consider the entire mass or weight of this alloy. So this is the mass of the first element. Since we are interested in the concentration or composition of this element 1, so its mass divided by the total mass of the alloy times 100. This is the weight percent of this element. How about if we are interested in the weight percent of element 2? So it will be M2 divided by M1 plus M2 times 100, and so on. So C1, this is the composition or the concentration of element 1. M1, this is the mass or the weight of element 1. M2, this is the mass or the weight of element 2. Also, we can represent this concentration or composition in terms of the atom number. How many atoms that belong to this element, how many atoms that belong to this element, or element 1 or element 2. So this is the number of moles of a certain element relative to the total number of moles in the alloy. As we discussed over chapter 2, we said that 1 mole, it should contain 6.023 times 10 to the power 23 atoms. This is known as the Avogadro's number. This is a certain number of atoms that would be located in 1 mole, known as the Avogadro's number, as we discussed in chapter 2. So it means that how many moles of atoms, because the mole, it counts how many atoms. It doesn't give the weight of this group of atoms, no, and instead it just gives the count of these atoms. So how many moles, we can count exactly how many atoms that would belong to this element 1 or element 2. So this NM1 stands for the number of moles of element 1. So NM stands for, the N stands for number, M stands for mole, number of moles of element 1, NM2 stands for the number of moles of element 2. So if you divided the number of moles of element 1 by the sum of the number of moles of element 1 and 2, assuming that you do have an alloy that is only made of 2 elements. So it means that in total we should divide by the total number of moles of the entire alloy. If it is made of 2 elements, so we're gonna sum 2 numbers. If it is made of 3 elements, you're gonna add the third number of moles of the third element, and so on, depending on how many elements forming this alloy. But since we are assuming that we have 2 alloys, so that's why we're already having here N1 divided by N1 plus N2. This is the number of moles of element 1 and element 2 times 100. And we are adding dash here just to distinguish between the concentration that is depend on the weight and the concentration of this element that depend on the atom number, or the number of moles inside this of atoms inside the alloy structure. We can do the same. How about if we are interested in the concentration of the second element? We just replace the NM1 with the MN2. You're gonna end up with the concentration of the second element. Right, so how about if we are interested in the conversion from the weight percent to the atom percent, or from the atom percent to the weight percent? These are 2 different approaches of representing the percent or the composition of an element within an alloy. So for example, if you already given the concentration of the first element and the concentration of the second element. Remember that this is only for an alloy that is made of two elements. You have element 1 and element 2, and it has a mass or a concentration of C1, and this has a concentration of C2, and this C1 and C2 were given as weight percents. These are the concentration of the two elements in terms of the weights. Already given to you. In the meanwhile, you knew the A1, A2, these are the atomic weights of the elements. And these atomic weights, as we discussed in chapter 2, in chapter 3 even, these are material properties. It means that for every element, it has its own atomic weight, which is well known. You can even Google it, you're gonna end up with this atomic weight for this element. So assuming that you have a certain metal and non-metal material with a certain atomic weight, everyone, so, and C1 and C2 were given, can we determine the concentration of element 1 or element 2, but in terms as atomic percent instead of being weight percent? Yes, according to this relation. So for example, the atomic percent of element 1 as C1 dash, we said that the dash what distinguish C1 and or the concentration based on the atomic percent or the weight percent. So based on the atomic percent, it is C1 A2 divided by C1 A2 plus C2 A1. Just observe the subscripts 1 2 1 2 2 1 and so on. So they should be swapping the subscript between the concentration and the atomic weights. You're gonna end up with this concentration based on the atomic number. The same thing, or the number of atoms to be more accurate. C2, the same thing for the other element, we can do the same. Just replace. The denominator would be the same, but the numerator would be changing. And instead of having C1 times A2, it will be C2 times A1 times 100. You're gonna end up with the concentration, or in terms of atom number or the atom percent as concentration or composition of element 2 within this alloy that is made only of two elements. Here, these relations are applicable only in case that you have an alloy that is made only of two elements. How about if we would like to convert from the atom percent to the weight percent? It means that the concentrations, the alloy was given also as two elements, but the concentration C1 dash, C2 dash, where are the concentration in terms of the atom percent were given to you. So you're gonna use almost the same expression, but observe the subscripts. When we convert from the weight percent to the atom percent, we are swapping these subscripts 1 2 for between the atomic weight and the concentration, but here we are keeping the same subscript. So C1 dash A1 divided by C1 dash A1 plus C2 dash A2 times 100. There, it's gonna be the same, but the only thing that you're just gonna change the numerator C1 A1, it will be C2 dash times A2. You're gonna end up with the concentration in terms of the weight percent in case that the concentration was given as atom percents. Make sense? So this is simply how we can convert between these two percents or ways of representing the concentration of the composition of the elements within the alloy. The question is, can we prove this relation, which is any one of these relations, like for example the first one, the conversion from the weight percent to the atom percent with respect to element 1. So can we prove this one? Yes. We said that this relation is applicable only in case that you have an alloy, and this alloy is made of only two elements, like element 1 and element 2. And in this case, C1, C2, which are the concentrations of the two elements in terms of the weight percent, were given to you. And we are interested in proving this relation, how much is C1 dash, which is the atomic percent concentration or composition of element 1 within this alloy. So if I ask you, what is let us assume first that the mass of element 1 is M1, the mass of element 2 is M2. Then if I ask you what should be the total mass of this alloy, so M uppercase stands for the total mass of the alloy, which definitely is going to be the mass of the first element plus the mass of the second element, as long as it is made only of two elements. So it is intuitive relation that you sum the two masses, you're going to end up with the total mass of the alloy. In the meanwhile, if I ask you to determine the mass of this alloy in terms of the concentration C1 or C2, the mass of every element. We said that this element has a concentration as C1, and this C1 was given, and C2 is also given. So what should be the concentration or the M1 in terms of the concentration? We can write this M1 equal this mass as the concentration of element 1 with respect to the total mass divided by 100. This 100 just to convert, because this C1 will be given as a percent. You got my point? Like this is the fraction of M1 within the entire mass of this alloy. This is the percent of M1 within this entire mass of the alloy. Like assuming that C1 it is 90% of the total mass. So it will be 90 divided by 100, which gives 0.9. The total mass of the alloy, you're going to end up with the mass of element 1. Makes sense. So this is also one relation. Also, can we determine M2? How about M2? It's going to be the same. It will be C2, the concentration of the second element, times the mass of this entire alloy divided by 100. This is going to give you another relation. Also, according to the definition of the atomic weight in chapter 2, this atomic weight it should equal to, it is somehow related to the number of atoms, or the mass or the weight of the number of atoms that would be used for forming 1 mole of the element. We said that this 1 mole has the Avogadro's number of atoms that form 1 mole of any element. So simply, we can we define this mass in terms of the number of moles and the atomic weight? Yes, we can determine or approximate the mass of element 1 at the number of moles of element 1 times its atomic weight. Because, for example, the atomic weight of this element 1, it refers to the mass of 1 mole of this element. It is related or can approximate the mass of 1 mole of this element. So if within this alloy, if you have this number of moles, what should be the total mass of this element? It will be the number of moles times the weight of 1 mole. So the A1, this is the weight of 1 mole of this element. And in case that you do have 10 moles, for example, of this element within this alloy, so it will be 10 times A, this is going to give you the mass of this element. So simply we can approximate the mass of 1 element inside the alloy at the number of moles that form this element within the alloy times the atomic weight, which represents the mass of 1 mole of this element. Can we do the same for the mass of the second element? Yes, we can say that this is the number of moles of the second element times the atomic weight of the second element. This is going to give us some other 2 relations. So according to relation 2 and 3, 4 and 5, can we determine the relation between, or M1 and M2, because this is M1 and this is definitely M1. So can we determine the number of moles of element 1 in terms of the other things? Yes. If you just put equation 2 equal to equation 4, you're going to end up with C1 times M divided by 100 A1. Agree? The same thing, the number of moles of element 2 will be C2 times the total mass of the alloy divided by 100 A2. So we end up with these 2 relations that will be considered like a key. Based on this relation, we can simply determine the concentration of the element 1 or even element 2 based on the atom percent or the number of moles. So simply, if I ask you what should be C1 dash, according to this definition, C1 dash is the number of moles of element 1 divided by the number of moles of element 1 plus element 2 times 100. So let us plug this in M1, M2 that we got here into this expression. So this is C1, number of moles of element 1 divided by NM1, NM2 plus MN2 times 100 equals. How much is NM1? We already got it by C1, M divided by 100 A1 divided by the NM1, which is C1, M divided by 100 A1 plus C2, M divided by 100 A2. Agree? So simply we can cancel or get rid of this 100 can be cancelled with the 100 with the 100. And the M can be cancelled with the M with the M. This is the total mass of the alloy, still the same. Then you can multiply the top and the bottom, or the numerator and denominator, times A1 times A2 on the top, and here also A1, A2, and this term will be A1, A2. It means that you're just gonna multiply all terms times A1, A2. So this definitely A1 will be cancelled with A1. Here A1 will be cancelled with A1. A2 will be cancelled with A2. So you're going to end up with this expression. at the end. So you're going to end up with C1E2, which C1E2, divided by C1E2, which is C1E2, divided plus C2A1, which is C2A1 times 100. This gives the expression that we got. So simply you're going to form these relations between the M1 and M2, and then you're going to end up or determine the number of moles of element 1 and element 2. Then you can simply plug them here into the expression that we define for the concentration of element 1, or the element that we are interested in proving its relation based on the atom percent. Then you just plug these data here and do some manipulation to this mathematical things. You're going to end up with this expression very simple. Make sense? So this is all what we discussed so far. We were discussing the point defects. We said that we do have three groups, three types or set of defects. Point defects, which are related to the vacancies, intersection and substitution of atoms. We spent enough time talking about the alloys and the concentration of the impurities inside the material structure and how we can calculate these concentrations. Now we can move to the second group of defects, which are the line defects. Make sense? Alright, so now let us move to the line defect. Line defects or linear defects, these are commonly known as dislocations. So the dislocation, it is a linear or one-dimensional defect around which some of the atoms are misaligned. Here we are talking about a group of atoms. Over the point defects, we were talking about that there is one atom that is missing in that point, which are related to the crystallographic point. That there is an atom that is missing, this is the vacancy, or one atom is going to be placed or replace another atom in another point and another lattice site or location. So this is known as point defect. But the line defect or the linear or one-dimensional defect, it means that there is a line or a plane of atom. This plane of atoms, it will be placed, or there is something wrong with this plane of atom, which is commonly known as dislocation. So the dislocation, it is a linear or one-dimensional defect around which some of the atoms are misaligned. So any changes, as we discussed, the objective in this chapter 4, we are highlighting any changing over the regular crystal structure that we covered in chapter 3. So any changes of this regular over this regular structure will be counted as a defect. One of them is the dislocation. And we do have in total three types of dislocation, either edge dislocation, screw dislocation, or mixed. Mixed, it means that it will be combination between the screw and edge dislocation. So what does it mean, dislocation? This is the definition of dislocation, but you should understand what is a dislocation is. So this is going to be much more clear as we discuss the edge dislocation or the screw dislocation. Make sense? But before we go through this definition of the edge and the difference between the edge dislocation and screw dislocation, let me bring to your attention this figure. This is how we see the dislocation inside the material structure through the TEM, the transmission electron microscope. When we look to this material structure, this is how we are going to see the dislocations. This is represent only one crystal, one grain inside the material. As we discussed before, that polycrystalline material, this is the material that is made of multiple crystals, and every one of these crystals could be considered as a grain. So the grain or crystal, they are the same. So we do have one grain or one crystal, you're going to have another crystal and so on, that form multiple crystals that form these crystals of material structure for a polycrystalline material. So if we just choose one grain, one crystal, and we're going to look at it through the microscope, how it would be seen? In the ideal situation, in the ideal case, this crystal, it should be seen like any other solid material. As you can see, do you see this surface? These surfaces like any other regular material. We will not see the atomic structure unless we zoom into this to see or increase the magnification factor of this microscope so we can observe and see the atomic distribution or the atomic structure of the crystal. But at this magnification factor, for example, which is 51,000 and plus, we can only see this crystal as a solid material, like any solid material that we experience in our life. So we're just gonna see any blank surface. In the ideal case, this image will be seen blank. There is nothing wrong. But how about of all of these dark lines? These dark lines which would seem like cracks, but in fact they are not cracks, they are dislocations. So these dark lines, these are the dislocations inside this crystal structure or inside this grain. So in the ideal case, in the perfect ideal case, the crystal structure or the grain structure will be seen over the TM, the microscope, the transmission electron microscope will be seen blank, like blank area, represent a surface of a solid material which is completely perfect. But in the real fact, in the real case, we should have some these dark lines which are very random. Every single line, every single thing of this line which would seem like cracks, this represents a dislocation inside the crystal structure or this grain structure. So all of these lines are different dislocations. So the dislocations are very high here in this crystal. So that's why we having this crack shape of the crystal. But remember, these are not cracks. These are just dislocations inside the grain structure or the crystal structure. Make sense? So the question is, what is a dislocation? This is how we are going to see the dislocation through the TM. But what is a dislocation? What is happening physically at the atomic scale that would result in the formation of these dislocation or would result in such an image of this material structure? The dislocation simply, it is like the addition. One of the simplest stuff just to understand what is a dislocation, let us explain the edge dislocation. Edge dislocation is an extra portion of a plane of atom. So it is extra portion of plane of atom. So it is not related to one atom. So that's why it is not counted as point defect, but instead it is plane of atom. So it is linear. This plane is going to form like a line. But this portion of the plane of atom, it is extra thing. Excess plane of atom with an edge that terminates within the crystal. Like for example, if we're gonna consider, let us consider this shape here. This is like a regular structure of the material. Assume that this is the regular structure of the material and this is the fact, and every one single line, whatever vertical line or horizontal line, represent a plane of atom because you do have so many atoms. So for example, you could have one atom here and another atom, another atom, another atom. So all of these atoms form plane, one single plane. In the real structure of these atoms, they should be tangent to each other. They are touching each other. Now, there is no space. I'm talking about the real atomic structure. And this is what distinguishes the hard core model and the hard sphere model and the reduced model of the crystal structure that we represented in slide 3 in chapter 3. So here we are considering the reduced model of the crystal structure that we are somehow assuming that there is a space, but you should understand that there is no space between these atoms. These atoms are arranged to form one plane which is perfectly straight. This is the ideal condition of the crystal, and definitely there should be another atom here, another atom here, another atom here, and so on. So this horizontal alignment of the atoms form another virtual horizontal plane of atoms, and so on. It means that every vertical line represents a plane of atoms. Every horizontal line represents a plane of atoms. So all of these planes of atoms, they are perfect. They are completely straight, nothing wrong. So this is the ideal condition of the crystal structure. But because of some reason, so let us reset back here. For some reason, like as I mentioned, this is like one atom and there are some other atoms underneath. So this is like multiple layers of atoms. But anyway, we do have like multiple layers of atoms, another atom that form a plane. So this vertical line is a plane of atom. This horizontal line, it is a plane of atom. As you can see, it is perfectly straight. Also, this is vertical. This vertical line or plane of atom, a vertical plane of atom, another vertical plane of atom, and so on. But for some reason, as you can see, if you can observe this half of plane, portion of a plane that is somehow squeezed inside the other plane, and it terminates, this is the condition, it terminates inside the crystal. This entire thing, it is a crystal. So this plane is not splitting the crystal entirely. If it splits the crystal, it will not be counted as a dislocation or edge dislocation. So the edge dislocation, the condition for it, that it should terminate inside the crystal structure. Like this is the crystal, this plane is not continuous. Somehow this plane ends in the middle, inside, and terminates inside the crystal, so that's why it will be counted as edge dislocation. So what is the edge dislocation? It means that you're gonna have a portion of a plane which is incomplete, that this portion you can deal with it like it is. We are enforcing, we are squeezing, we are inserting by force this plane between the other plane of the regular structure of the crystal to form a dislocation, to form an edge dislocation. This plane, when it is inserted there, it will be seen as a crack, as a black line in the micrograph. Make sense? It will be seen in this way. Every one of these lines doesn't indicate only one plane that is already squeezed. No, it indicates like multiple of planes, multiple of dislocations that form this line together. Okay? It means that there are lots of planes that already squeezed or enforced between the different planes inside the crystal structure, and the condition is that these planes are terminating inside the crystal structure to form an edge dislocation. Make sense? So this thing is known as edge dislocation. This kind of defect, it is an edge dislocation. What is the problem of this edge dislocation and why we are considering it as a defect? Because it do changes over the regular structure of the crystal that represented here. This is the ideal crystal structure, but because of the addition of squeezing another plane as shown here, do you see this plane? This is an edge dislocation. This is the first plane, and there is a plane here, another plane, and for some reason we are inserting an excess or extra plane, half of plane, not a complete plane, and it terminates here. So this is the end of this plane that is squeezed between the other planes. So this will result in a distortion in the crystal shape. So as you can see, somehow it is expanded from the top in comparison to the bottom surface. In addition, you're gonna have some that this plane, it will not be straight anymore, it will be deflected. There is a distortion over this plane. This distortion will be counted as a defect in this crystal structure. Make sense? So edge dislocation causes lots of things. One of the things, it presents or results in localized lattice distortion. So what is a lattice distortion and what does it mean localized? Lattice distortion, as I said, the plane will not be straight. The plane of atom, it will not be straight anymore. So this would be counted as a form of the lattice distortion. Or the entire crystal will be shaped. The region around this dislocation will be differently represented. The arrangement of atom will be different. This is what does it mean, a lattice distortion. So we can consider the lattice distortion as distortion or a change over the regular distribution of atoms inside the crystal, or also we can consider this lattice distortion as distortion in the straightness of any atomic plane within the crystal structure. That this plane should be straight, but it won't gonna be straight anymore. Why? Because of the dislocation. So the lattice distortion is a result of the dislocation. One of the things that result because of the edge dislocation is a lattice distortion. This is one thing. But the key condition that it should be localized. What does it mean to localized lattice distortion? Localized, it means that this distortion, it is just around the dislocation, but as we go far from the dislocation, this distortion will be negligible. There is no lattice distortion anymore. Just to explain to you what does it mean localized lattice distortion. A localized lattice distortion, for example, if let us assume that you do have very wide lattice that has so many planes, one plane, another plane of atom, and so on, so many planes of atoms, and there is one of the planes of atom, like this is a plane of atom that should be located here, and as we try to insert half of plane or a portion of a plane of atom by dislocation, so this is the dislocated, this is dislocated plane of atom. This dislocated plane of atom, it will push this plane to the right and it will push this plane of atom to the left to squeeze itself inside, as already shown here. So that's why the width from this point to this point, it became larger than the width from these 2 points. Make sense? So this will result in a lattice distortion. This plane will not be straight anymore. But this is very close next to the dislocation. But as we go far, so we can have some kind of distortion within this plane, another distortion with this plane. But as you can see, as we move far from the dislocation region, the distortion in the lattice or the crystallographic plane, it will decreasing. Like even we're gonna end up at the very far field or area from the dislocation that we're gonna end up with this plane almost 100% straight. So that's why this, what does it mean? It is localized. Localized, it means that the distortion or the non-straightness of the planes will be surrounding within the plane that are surrounding very close to the dislocation, and as we move back or far from the dislocation, these planes will become straight one more time, or the effect of this lattice distortion will be decreasing as we move far from the dislocation. This, what does it mean that we do have localized lattice distortion? It means that this distortion in the lattice or the change in the straightness of the crystallographic plane will be only around for the planes which are surrounding the dislocation, and as we move far from the dislocation, this non-straightness things will be very negligible, and in that case we're gonna end up with the straight planes. Make sense? This, what does it mean? It is localized lattice distortion. Also, edge dislocation would result in atoms above the dislocation line are squeezed together, while atoms below the dislocation line are pulled apart. What does it mean this? For example, assume that these lines represent like strings or springs, to be more accurate. Okay? So when you try to squeeze this plane of atom in the middle, what should be happening to these springs between these atoms? So these springs here will be compressed. This spring will be compressed. Right? If this is a spring and you try to insert, so in the regular case, all the springs will be tight. The same tension, will have the same amount of force or amount of tension between them. Assume that these like strings or springs. So when we try to add one extra portion of a plane within this crystal, so these strings or these springs will be compressed. So that's why they are squeezed, because you are squeezing something in the middle. It means that these atoms will be squeezed. So that's why the atoms above the dislocation line, what is a dislocation line? This little red thing is known as a dislocation line, and we're gonna discuss this. So this little thing represents a dislocation line, and next to this line we can slice or we can divide this crystal into two parts. One part which is above the dislocation line, and there is another part which is below the dislocation line. All the atoms which are related or belong to the upper part or above, located above the dislocation line, all of them are squeezed together or pushed together. It means that the force is between them like kind of compression force. They are compressed together because of what? Because of the dislocation. You are inserting extra plane, so it became more crowded. More crowded, it means that they are squeezed all together. But on the other side, the atoms below the dislocation line, they are pulled apart. It means that this is string that found between these atoms that located in the lower side will be stretched, will be pulled. So that's why it is pulled apart. It means that there is more tension located below the dislocation line. So what does it mean this? This indicates that above the dislocation line, the material, it is compressed. There is a compression above the material, above the dislocation line, but below the dislocation line, there is a tension. And this is another form of lattice distortion. This is another form of a defect, which we are going to discuss with more detail, especially in chapter 7 or over the next chapters. So this is also another form of defect, that the stress 4 is different than above the dislocation line. It is different than the stress type below the dislocation line. The difference in the stresses, there is compression. Below the dislocation line, there is a tension. This difference results in some defects and more, and results definitely will affect the mechanical properties of the material, as will be discussed over the next chapters. Make sense? So this is also one of the reasons, why we are studying why the dislocation is a big deal. It is one of the serious defects, an important defect that significantly influence the mechanical properties of material is the dislocation, especially the edge dislocation. Make sense? So the edge dislocation results in localized lattice distortion. It makes atoms above the dislocation line squeezed or compressed together. It means that will result in a compression stress. But below the dislocation line make atoms are pulled apart, which results in a tensile stresses within these atoms below the dislocation line. And remember, these things are just around the dislocation. But as we go far from the dislocation line, or the dislocation plane or the dislocation area, these defects will be eliminated or will be decreasing. So the magnitude of the distortion is maximum at the dislocation line and decreases with the distance away from it. What does it mean, the magnitude? The magnitude of the dislocation, it means that the magnitude of the distortion. It means that the distortion, it can be measured, right? Once we said something has a magnitude, like the force, it has a magnitude, it means that we can measure the force. Right? So the same thing, the distortion in the lattice structure, it can be measured by something that we name as Berger's vector. So the Berger's vectors, this is the measure that quantifies how much of distortion that it would be result in this crystal because of the dislocation. What does it mean measure? Like for example, if we're going to talk about a force, it is a measure. The velocity is a measure of how the object changes the distance with time. The acceleration is another measure that represents or measures or represents the change in the speed of the object with time. So these physical quantities that we experience in life, they do have measures that we are using as engineers to represent them. One of these measures that are related to the material science is Berger's vector that measure the distortion that would be resulting in the material due to any defect, whatever it is, especially if it is dislocation defect. So the Berger's vector, it is a measure that is used for determining the distortion because of the dislocation inside the crystal structure. So the magnitude of this Berger's vector is going to decrease as we go far from the dislocation, and it will be maximum at the dislocation line and decreases as with the distance away from it. Very far from the dislocation line, very far from the dislocation line or the dislocation region, as we mentioned, the crystal lattice is virtually perfect. There is no defect that should be there unless there is another dislocation that would result in these defects. So these are some of the things that would result because of the dislocation. And remember, this dislocation, this type of defect is very important, and we're going to discuss this dislocation one more time with more detail when we discuss the strengthening mechanism. That this dislocation, it is strongly related to the plastic deformation of the material and the strength of the material. This will be discussed over the next chapters. Make sense? So going back to the edge dislocation line. So since we are talking about edge dislocation, this little small symbol indicates is known as the dislocation line or the edge dislocation line. So this symbol indicates that there is a dislocation, and the type of this dislocation, it is dislocation, edge dislocation, and it refers where you're gonna find the plane. That it should be this horizontal line indicate, or this vertical line in this way, and mean that to this, the plane, it will be inserted between the other parallel plane in this direction. So this is known as the dislocation line. Make sense? Also, something that you should understand about the Berger's vector, but I'm going to discuss this Berger vector, but let us move to the screw dislocation. We said that dislocations are three types. We have edge dislocation, screw dislocation, and mixed dislocation. The edge dislocation, that you're going to have a portion of a plane that it will be squeezed or inserted between different planes, resulting in these defects. And the key condition that this plane, it should be terminated or terminates inside the crystal structure. But if it is complete and go from one end to the other end of the crystal, it will not be counted as edge dislocation. It could be counted as a boundary between two different crystals, okay, or grains. But anyway, the screw dislocation is another form of the dislocation. The screw dislocation also is a linear defect, one-dimensional defect like the edge dislocation, in which one portion of the crystal is shifted either one or more atomic distance. So this distance, it will be considered as a measure of how severely this crystal has been distorted because of the screw dislocation. It is a measure of the distortion in this crystal because of the screw dislocation. But anyway, you're gonna find one portion of the crystal will be shifted. This would end up with like a screw or twisting in the crystal, because one portion, like as shown here, this top portion, this entire portion, top portion of the crystal has been rotated with respect to the bottom portion, and this resulted in a shift or a screw dislocation. So the screw dislocation is one portion of the crystal is shifted one or more atomic distances relative to the other portion of the crystal, and this is what defines the screw dislocation. As I mentioned, like you just holding this crystal and you rotating one portion to the other portion. Make sense? This is very similar to the Rubik's Cube. Like if, for example, if you're just gonna have one layer of this cube and give it rotation with respect to the other portion, so one portion will be rotated with respect to the other, this is edge dislocation. I'm sorry, this is screw dislocation. It is very similar to this Rubik's Cube thing, but as I mentioned, that you're gonna find one portion of the crystal will be shifted with respect to the other portion. But there is a little bit different. I just put this Rubik's Cube thing just to understand what does it mean, a screw dislocation, but you should understand that this top portion, it is not physically rotating like the Rubik's Cube. The Rubik's Cube rotates about a point that is located in the center, and all the top layers will be rotated. This is what is happening in the Rubik's Cube. But here, this is not the case. Like you're gonna have one portion, just the front portion, and you're just gonna shift it right or left. It is not completely twisted. It is not completely screwed, as the case of the Rubik's Cube. So there is a difference. It is almost the same concept, yes, but there is a difference that you should understand between the Rubik's Cube, rotation of one layer or one portion of the Rubik's Cube, and the physical real screw dislocation. In the screw dislocation, we're just shifting. So that's why we are giving the name as shifting, not rotating, to be more accurate definition of the screw dislocation. That we just shift this top part of the dislocation of the top portion of the crystal to the right or to the left, and keep the other portion. So it would seem like it is screwed. It would seem like it had been twisted or rotated. But physically, it is not twisting. Physically, it is not rotation. It's just shifting. So that's why we are using the shift word. So you should understand, it is almost the same concept like the Rubik's Cube, but there are some differences between the Rubik's Cube, the rotation of one layer of the Rubik's Cube, and the screw dislocation that exists inside the crystal structure. Make sense? How about the dislocation line? We said that there is a dislocation line that, like the dislocation line for the edge dislocation, which had this symbol. But here, the dislocation line in the screw dislocation, it is represented as a line that is conceded over the edge, that it should be there. Like there should be an edge here. So this is the dislocation line. This line, it is the dislocation line. Then we are giving a rotation that indicates the direction of the dislocation. For example, if you draw the dislocation line here and you give the rotation, the direction of rotation should be rotating to hit the top surface of the other or the bottom part. Like there should be a surface, extra surface that is going to generate. You got my point? So this is how we define the direction of the dislocation. But for example, if we switch the direction of the dislocation, it means, so based on this direction of the rotation over the dislocation line. So the dislocation line is just the line. So this line represents the dislocation line. And then we are giving a rotation to indicate the direction of the dislocation, to indicate the direction of the screw dislocation. Why? Because if you're handling this crystal, I can shift it to the right or to the left. So these are two different directions. If you shift to the right, you should have the direction as represented here. You're gonna give the rotation till you hit. It means that there is a surface that is going to generate. that there is a top surface. Here I'm talking about this surface that is going to generate once we shift to the right. But if you shift to the left, the surface will be formed on the other side. So this will result in a different direction. In another direction, it means that the direction will be switched, or it will be the same if you decided to draw over the other side. I will not go through the details about this direction, but this is something that you just to know, just for your information, how we can define the directions of these dislocations, but you are not required to do any calculation or anything regarding these directions of the dislocation. But anyway, there is also a dislocation line, like the edge dislocation, it has a dislocation line. Also, the screw dislocation has a dislocation line, and we can even define the sign of the dislocation. It's known as the sign of the dislocation or the direction of the dislocation. Okay, the same thing for the edge dislocation. It could have a sign or a direction that indicate what is the direction of the dislocation. It means that this plane is inserted in this direction, and this vertical line indicates the direction of this dislocation. Because as I mentioned, as we explained here, this dislocation, for example, if we do have this dislocation line, if it is represented down, this means that the compression will be below the dislocation line and the tension will be above the dislocation line. But this direction, which is already directed up, it means that the compression is above the dislocation line and the tension will be below the dislocation line. It means that this dislocation has a direction. So anything, this dislocation will result in some distortions in the crystal structure, and we can measure this distortion by the Berger's vector, which it is a vector. It means that it should have a magnitude and direction. So it is a vector, it means that it has a magnitude and direction. It means that we can define the distortion in the crystal as a magnitude with a value and direction depending on the dislocation line. The same thing here, there is a specific direction for the screw dislocation that depend on this direction of rotation over the dislocation line for the screw dislocation. Make sense? Alright, so what is the Berger's vector, which we gonna refer to it as B? We will not do any calculation. This is just for your information or just to know what is a Berger's vector. This is some of the requirements, but basically material scientists are using this Berger to identify the distortion or to measure how severely the crystal structure has been distorted because of a dislocation. So it is a measure, as we discussed, that identify the amount of distortion that it would be generated into a crystal because of an edge dislocation or a screw dislocation. So Berger's vector, it represents the magnitude. So that's why it is a vector. And as we knew from physics even, that any vector quantity, it should, to be fully described, it requires a magnitude and direction. So that's why it is a vector. It has a magnitude and direction of the lattice distortion. It represents, it measures the lattice distortion resulting or that result from a dislocation in a crystal lattice or a crystal structure. Like you'd have a crystal, as I mentioned, you'd have an edge dislocation or a screw dislocation. How we can measure the lattice distortion upon these dislocations, this is known as the Berger's vector. And it is somehow related to the material properties. Like we can relate the material properties to the Berger's vector. As this vector increases, this indicates that there are more dislocations, there are more lattice distortion, and the material properties somehow are related to these distortions in the lattice structure. And that's why we are as material scientists, for example, we are defining these Berger's vector for the different lattice distortions so we can relate this Berger vector to the material properties. We will not do this connection between the Berger's vector and the material properties. We aren't gonna do this, but anyway, at least you should know what is a Berger's vector and how we can use this vector to measure or identify the lattice distortion based on for a edge dislocation or screw dislocation. For an edge dislocation, it is perpendicular, whereas for a screw dislocation, it is parallel to the dislocation line. We said that for the edge dislocation, there is a dislocation line like this one. This is the dislocation line. And the dislocation line for the screw dislocation is gonna be like a kind of horizontal line that goes through the material in this way, and it will be rotating in this direction, so it would hit over this surface, that it will be appear up on shifting one portion of the crystal to the right, as already shown here in this screw dislocation. So this type of dislocation, it is a screw dislocation, but definitely this is an edge dislocation. Make sense? So the Berger vector, it measures, for example, if we squeezed, like in the edge dislocation, if we squeeze only one plane between other two planes, so there would result a distortion in the lattice, and the magnitude of this distortion, it would be measured by B at the magnitude of this vector, and in many cases it will be conjugate to one lattice distance. It means that it will be conjugate to only one lattice. How about if we added more dislocations in the same place? So the distortion in the planes, the swerving in these planes, it can be measured by a distance, a lattice distance, and this lattice distance is going to be represented in the Berger's vector, which will only be one lattice. If we added more planes, this Berger vector, it would exceed one lattice site. It could be increasing like into two lattices or three lattices. It means that like two distances or three distances and so on. So this is the magnitude when we talk about the magnitude of the Berger's vector. The same thing, the magnitude here, we are shifting only one lattice site. We just shift one crystal. Or one unit cell, I'm sorry, we just shifted one unit cell, but we could shift, for example, we could have more shift, like we could have like 2 unit cell shifting or 3 unit cells and so on. So in that case, the magnitude of the Berger's vector will keep on increasing as we increasing the shift to the right with one lattice or two lattice or one unit cell or 2 unit cells and so on. So how many unit cells, how many lattice sites that we shift this portion with respect to the other one, or how many sites that or unit cells that these planes have been swerved or curved, this can be measured by the magnitude or identified by the magnitude of the Berger's vector. So this is for the magnitude. How about the direction? The direction as written here. For the edge dislocation, the direction of the Berger's vector, it will be perpendicular to the edge dislocation line. This is the dislocation line, and as we said that this vertical line indicate where is the pressure, the compression side, or where is the dislocation plane, where this plane will be dislocated. So we do have a dislocation that is located here, and this line indicates the sign and the direction of this dislocation. So the Berger vector, it should be perpendicular to this vertical line. We said that this horizontal line, this is like a separate line. This is like a datum, like a reference, and you're gonna have a vertical line. This vertical line directed or defined where you're gonna find the edge dislocation. So the direction of the Berger vector, it should be perpendicular to this line. So this is the main line that we are talking about, not the horizontal line. You got my point? So the Berger's vector will be perpendicular all the time. The direction of the Berger's vector for an edge dislocation, all the time it is perpendicular to the dislocation line. But it is parallel to the dislocation line for the case of screw dislocation. For the case of the screw dislocation, this is the dislocation line. This is the line. And as you can see, the direction of the Berger vector, it is parallel to the dislocation line. So in the screw it is parallel, but in the edge dislocation it is perpendicular. To demonstrate this further, as we discussed before, this is the ideal crystal structure. Nothing wrong. All the planes which are vertical, horizontal planes, they are perfectly straight. This is the ideal condition of the crystal structure. But for some reason, because of an edge dislocation, this is an edge dislocation that is already included here. So this is the dislocated half of plane that terminates. This is the condition inside the crystal itself. So this will result in a distortion in the shape of the ideal, change over the ideal shape and form of this crystal. This crystal, it is perfectly square. So now it has like a different shape because of the addition of another plane. So as you can see, if you just compare the difference between this edge, for example, this is one of the methods or ways that we can estimate the magnitude of the Burgers vector, and this edge. The difference between these two edges is going to give us an idea how much of distortion that have been resulted because of the addition of this dislocation. We added some dislocations here. It could be only one plane or multiple planes. We are not sure. So if we just measure the difference, we can have an idea how much should be the magnitude of the Burger vector. So the magnitude is going to be, if you just compare the difference, calculate the difference between these two sides or these two length values, you're gonna end up with you're gonna end up with the magnitude of the Burgers vector, which will be like one lattice side, like one unit cell as a magnitude. Also the direction, what type of dislocation that would have here would have only the edge dislocation. So the direction of the Burger vector, it should be defined in a direction that is perpendicular to the line action or the dislocation line. The dislocation line, it should be drawn in this way, like it terminates here. So this line, horizontal line, indicates the termination side, and this is the direction of the dislocation. And as you can see, it is perpendicular to the dislocation line. This is for the edge dislocation. How about the screw dislocation? The screw dislocation, the dislocation line will be drawn here. Like as you can see, this, if we slice this crystal into two pieces, into two parts, one part to the left, one part to the right. So the left side, as you can see, it is kind of shifted up. It's going up. With a certain distance, this distance, it is only one box or one square, which indicating only one unit cell. It means that the magnitude of the Burgers vector, it will be only one unit cell. It is conjugate to one unit cell. And the direction of this unit vector, it should be going up. This is what we understand from the shifting that is happening. And as you can see, because this is a screw dislocation, it means that the direction of this Burger vector, it should be parallel to the dislocation line, and this is what is happening. This is the case. We do have the direction of B, it is parallel to the dislocation line. Make sense? So far we discussed two types of dislocation, but we said in general we could have edge, and these are the only types of dislocation that we have: edge dislocation, screw dislocation, or it could be mixed. Mixture, it means that it is like a mixture of the edge dislocation and the screw dislocation, that both are happening or taking place at the same time within the same crystal, like the case of the mixed dislocation. So the mixed dislocation, it is intuitively, it is combined edge and screw dislocation. There is the combination of both in one crystal happening at the same time. Most dislocations found in crystalline materials are probably neither pure edge nor pure screw. It is hard to find a pure edge dislocation or a pure screw dislocation. In many of the cases, we are having these combined dislocations. As we discussed here, for example, in this crystal or this grain, in this TM image, we do have so many dislocations. What type of dislocation? They are combined. There are edge dislocation, there are shift dislocation, so there are lots of things that happening here. So in many of the cases, this is what is happening in reality, that we do have mixed dislocation. But we can break this mixed dislocation into either an edge dislocation or a screw dislocation, so we can study this complicated dislocation type. But exhibit components of both type as edge and screw dislocation as mixed dislocation. For metallic elements or materials, the Burgers vector for a dislocation points in a close-packed crystallographic direction and will be of a magnitude equal to the interatomic spacing. As we said that the magnitude, as we discussed here, the magnitude of Burgers vector, it depends on one unit cell or two unit cells and so on. So it is measured by the lattice distance or lattice spacing, which indicate the A vector value, if we are talking about a cubic crystal, for example, that we discussed in chapter 3. This is the magnitude, and all the time it is directed in the crystallographic, the close-back crystallographic direction. This crystallographic direction is the one with the highest linear density. So that's why we discussed the linear density in chapter 3, and we knew how we can calculate this linear density, because this is one of the things that the direction of the Burgers vector, it is oriented all the time over the line or the direction with the highest linear density, which is known as the closed back crystallographic direction. We are going to discuss similar thing in the next chapters with more detail when we discuss how these crystal structures are related to the strengthening mechanism of the material and how these dislocations are related to the strengthening mechanism of the material. Make sense? But for now, the thing that you should understand in the case of the mixed dislocation is what will be the shape of the dislocation line. We said that the dislocation line, it would be represented in this way. For the case of edge dislocation, it will be like a line that is intersecting at the end point of the dislocation or the shifting for the screw dislocation. How about if we do have a combined? In the combined, in that case, the dislocation line will keep going in a curve. It will be curved. It will not be straight line like the edge or the screw. So that's why it's kind of complicated thing. Why? Because in this side, as you can see, this side at this point or lattice side, this represents like a pure screw dislocation. On the other side, we do have a pure edge dislocation. So we do have here an edge dislocation over this plane, right? Like this extra plane, and over this side we do have a screw dislocation. So when we transfer from the 100% screw dislocation to the 100% edge dislocation, in between, definitely we're going to have a mixture of the two dislocations. So that's why we are talking about the mixed dislocation. So that's why in this case, this line, this is the line for this is the direction of the dislocation line for the screw dislocation, and it should be for the edge dislocation, it should be this is the dislocation line or the direction kind of, which should be perpendicular because the direction or perpendicular to the dislocation line. So as you can see, it should, for the mixed dislocation, it should be curved because we have to swerve or switch from being in this direction to follow another direction, in a perpendicular direction, to go to the perpendicular direction. So that's why in general the dislocation line for the mixed dislocation will be kind of curved. And the direction of the Berger's vector, this B, will be, as already shown here, it's going to be much more clear here. This is the edge dislocation, this is the screw dislocation side, and it will be curved in between. And the Berger vectors, as you can see, it will be, the Berger's vector, it will be all the time having one direction, moving from this lattice side to the other lattice side, or from this point to the other point. It will be all the time. Over this side, it should be parallel to the dislocation line because this is the dislocation line in case that we are talking about pure screw dislocation. So it should be parallel to the screw dislocation. Over this side, it should be perpendicular. So that's why here it should be perpendicular to the dislocation side, which is already perpendicular to the dislocation line over the edge dislocation. In between, since the dislocation itself is the thing, the dislocation line is the thing that curves or rotates or changes direction, this is gonna make the direction of the Berger's vector all the time directed in one direction, which is this direction. What is this direction? Is known as the closed back crystallographic direction, which is related to the linear density, the direction in the crystal structure that depend on the crystal structure with the highest linear density. We're gonna have this direction of the Berger's vector. This is how we can identify the direction or the magnitude of these Berger's vectors in the metallic crystals. Make sense? All right, so now let us move to the last group of defects, which are known as interfacial defects. As we discussed, we do have three sets of defects. We do have the point defect, we do have linear or line defects like dislocations, which are commonly known as dislocations, and planar defects or interfacial defects like the grain boundaries. But in addition to the grain boundaries, there are other forms of these planar or interfacial defects, which will be covered here. So an interfacial defect, it is a boundary, or interfacial defects are boundaries that have two dimensions and normally separate regions of the material that have different crystal structures or even different crystallographic orientation. So interfacial defects, it is different types that would be grouped as interfacial defect. But interfacial or planar defect, it means that it is related to two-dimensional things. So if we compare the point defect or linear defect or planar defect, as you can see, the point defect, it is related to a crystallographic point, location of an atom, as we mentioned. The linear defect or line defect, it is related to the linear density, as we discussed the Burgers vector, for example. So it is linear thing. It is related to one line represented in one direction inside the crystal structure. But the planar density, the planar defect or the interfacial defects, it is related to a plane, a crystallographic plane, not a crystallographic direction. So again, the point defect, it is related to crystallographic point that we have covered in chapter 3. The line defect, it is related to a crystallographic direction that we covered in chapter 3, but interfacial defect, it is related to a crystallographic plane that have been covered also in chapter 3. Make sense? So all the chapters are connected together. So interfacial defect, it is a boundary that has two dimensions, and it is normally used to separate two regions of materials, of the material. Like you do have one crystal, that you're going to have one region of the crystal, one part of this crystal, and there is another crystal or another part of the crystal, whatever of the same crystal or two different crystals. Like you may have one crystal and another crystal, so there should be a boundary between them. There should be something between them. This something that's separate, that make this crystal is different than this one, or this region is different than this region, or this part of the crystal is different than this part, is known as interfacial defect. So it is mainly used to separate two regions or two parts or two crystals within the material, whatever these two crystals of the same crystal structure or two different crystal structures. But if they do have the same crystal structure, definitely they're gonna have different crystallographic orientations, and we're gonna discuss this crystallographic orientation and how we can define this. Okay, so simply an interfacial defect, it is a boundary that has two dimensions, and it is normally used to separate two regions, two parts, two crystals inside the material that have two different crystal structures, or even if they do have the same crystal structure, it will be used to separate two different crystallographic orientations. And this is the important thing, especially for polycrystalline material and especially for grain boundaries. Types of these interfacial defects are many, like external surfaces, like grain boundaries, twin boundaries, stacking faults, phase boundaries. So all of these are different forms of interfacial defects. We are going to discuss some of them, like for example, external surface, grain boundaries, and twin boundaries. But these are other types that also could be exist as interfacial defect, just to know about them. So what is an external surface? External surface, from the name, it is the external surface of any crystal. It is an external surface that is the exterior at which the crystal structure terminate. Like for example, if we're gonna talk about any crystal, we said that this crystal consists of many unit cells and that represent the structure or the way of arranging the atoms. So originally the crystal consists of many atoms. So millions, trillions of atoms are forming one crystal in this site, for this size, for example. So if we're gonna look to the crystal, is it seem a very perfect cubic shape as we used to see or represent this crystal in chapter 3? No, it will be seen like any with an external surface, and this external surface will be very random surface, and it has so many other things. So for example, if we're gonna look to any regular crystal, it will be seen like with very broken, not a straight surface. And this crystal has so many atoms. Some of these atoms would be located over the external surface of this crystal, which we could name them as surface atoms. And there are some other atoms which are located in the core, inside the crystal itself. Okay? So when we talk about the external surface, it is the exterior. So the external surface will be the exterior of this crystal. This is the exterior of the crystal. Here we are talking about this surface, which is the exterior of the crystal. This external surface at which the crystal terminates, because this is what sign that this is the end of this crystal. Atoms belong to the crystal surface, which are known as the surface atoms, are only underbonded. What does it mean this? Referring to chapter 3, we said that there should be a bonding forces between all of these atoms to form a crystal, to form a material. So if we're gonna select, let us assume that this is the surface. make it like an ideal surface, nominal surface, and you do have some atoms which are located over this surface. So these are the surface atoms, and definitely there should be other atoms which are located in the core. So if I ask you, what is, for example, if we choose one atom that is inside the crystal, like this one, this atom, it has neighbors, and this what defines the coordination number that we discussed in chapter 3. These are the neighbors to this atom. So there should be some forces or bonding force that is going to generate between this atom in the center and all other atoms that surrounding it, right? So we're gonna say that this atom is bonded from everywhere, from all directions. It is bonded. It is bonded from this direction and this direction. So over the 360 degrees surrounding this atom, it is bonded from all directions. But if we're gonna choose the atom that is located over the surface, there is no atoms above this atom, but all the atoms are located below the atom, below the surface, right? So there should be some interaction. There is a bonding force here, another bonding force, another bonding force, another bonding force. But there is no bonding interactions above this atom, above the surface, because there is no more atom. These are the external atoms and nothing more. So this means that these atoms which are located over the surface, they are under bonded. What does it mean under bonded? Or under coordinated or under connected to the under atoms. But there is no bonding above this atom, above this surface. This what result in some excess energy. This will result in a higher energy state than the atoms in the interior. That these atoms that located over the surface will be in a higher energy state more than the atoms that located in the surface. And this change or difference in the energy level as for this atom than the atom in the core is counted as a defect inside the material structure or inside the crystal structure. We said that anything that is different than the ideal case, it will be counted as a defect, whatever it is. It could be in the form of a distortion in the lattice. It could be in the form of a change or a difference in the strain. It would be a form and a change or a difference in the energy level. Like these atoms which are located at the surface, they will have energy that is different than the energy than any other atom that would be located in the core of the crystal. This difference in the energy level, this what results in the surface tension. For example, we said that in liquids, we do have the surface tension, like in water. This surface tension, the main reason behind it, the same terminal, the same concept, that the atom that located at the surface, they are under coordinated, so will be a different energy level for these atoms. These atoms will have excess energy that comes from these extra coordination. So for example, for this atom to be in equilibrium, the excess energy, the surface energy will be different. That this bonding force between these atoms on the top will be higher than the other bonding forces. Like this bonding force is like this one, like this one, like this one. But the bonding force which is represented by green here, it will be higher. Why? To achieve equilibrium. To compensate for the missing bonding that it should be above the atom. But here, for this atom that is located in the core, all directions, in all directions, the bonding force is the same. So it is already in equilibrium and everything is even, all the bonding force are equal. But for the atom that is located over the surface, they are only connected from the blue atoms. There is no atoms on the above, so all the connections are under. So that's why it is known as under coordinated or under bonded. But there is no bonding on the top. So to compensate for this missing bonding force and to achieve a static equilibrium like any other atom inside the core, this would need that this bonding between all the atoms over the surface should be higher to compensate for the missing one, to account for the missing one, to collect the missing one. So that's why this would result in a higher energy, more bonding than the usual that we used to have for any regular atomic structure. So that's why this is counted as a defect inside the material structure. It is good in some application and it is bad in some other applications, but we have to consider it. So the external surface, this is the external surface, or that the exterior of the crystal that terminates the crystal, that indicate that the crystal structure has been terminated. Atoms that located over the surface, which are known as the surface atom, they are only under coordinated, bonded, and that's why there is a higher energy level or state for this atom than the interior atoms. And the excess energy of the surface tend to deform the surface. This would result in a deformation in the surface. So the surface will not be perfect straight. It will be curved. Because of what? Because of this excess energy. Because of these tension forces, that excess energy, the straight will not be perfect straight, it will be curved. It means that there is another effect of these surface forces or surface energy or external surface, that it would result in a curved surface or distorted surface or deformed surface, and that's why it is counted as a defect. Make sense? So this is one of the interfacial defects, which is known as the surface effect. Another type is grain boundaries. What are grain boundaries? It is from the name. It is grain and it is a boundary for the grain. Any crystal, as we said, it is any grain, it is just a crystal. Like for example, if we're gonna look to any polycrystalline material, this is a typical example of a polycrystalline material. As we discussed before, this polycrystalline material, it has a granular structure. What does it mean, granular structure? It means it consists of many grains. So as you can see, every single box like this thing represent one grain. This is another grain. This is another grain, and so on. So we do have so many grains, and this is an image of TM image of a polycrystalline material, whatever it is. So the material will be seen like it consists of so many grains, and as you can see, these grains are random. Random in terms of size, in terms of orientation, in terms of shape even, right? There is no uniformity that we could observe here for this polycrystalline material. Make sense? But remember that these grains are very tiny things. This is the polycrystalline material that you can observe, any metal material that you can see life it is in this form. Any aluminum, any steel material, any copper material, anything, it will be seen in this way. This is a polycrystalline material. But we are not seeing the material we cannot see these grains unless we look at it through the microscope. It will be seen like any blank surface, that perfect surface, we will not observe these grains. But when we look at it through the microscope, as we discussed, we can see these grains. Every one of these grains represent a crystal. So it is one crystal here, there is another crystal, another crystal, another crystal, but these crystals, they do have the same crystal structure. Here we are talking about a pure or a conventional polycrystalline material. All of these crystals, they do have the same crystal structure. That the crystal structure for this crystal, for example, it could be like FCC crystal structure. This will be the same crystal structure, FCC. All of them are FCCs. Make sense? But why, since all of them, they are representing different crystal structure, why are we still dealing with them as two different crystals? Yes, because there is a boundary between them. There is a boundary that makes us to distinguish that this is one crystal, this is another crystal. They do have the same crystal structure, but they are different in terms of crystallographic orientation. So going back again to the definition of the interfacial defect. What does it mean, an interfacial defect? It is something, anything that make one part is separate from the other part. What make one crystal is different than another crystal, or separate from another crystal. That what makes one grain is different than the other grain. This would be counted as an interfacial defect. Whatever these two crystals or two grains, they do have the same crystal structures or two different crystal structures. In case that they do have the same crystal structure, the difference will be in the crystallographic orientations. And we are going to discuss what does it mean a crystallographic orientation. But for now, the grain boundary is something that separates two grains or crystal. We said the grain, crystal, they are the same thing, having different crystallographic orientation in a polycrystalline material. This indicates in many of the cases, these grains, they do have the same crystal structure. There is no difference in terms of crystal structure, but the difference is in terms of the crystallographic orientation. What does it mean, a crystallographic orientation? To explain it, let us consider this broken structure atomic structure of this polycrystalline material. Like as you can see, this group of atoms, all of these are the same atoms of the same elements. It means that this is like pure metal material. But this group of atoms, they are arranged in this way. Like you do have this is a plane of atom, this is another plane of atom, another plane of atom. So they do have a certain crystallographic orientation. What does it mean, orientation? They do have a certain arrangement. If you're gonna look to the other atoms, like these atoms, they are oriented differently. Like this is the plane of atom, this is another plane of atom, another plane of atom. So as you can see, this group of atoms, this cluster of atoms, they are arranged this way. And this other group, they are arranged forming crystallographic planes over this direction. So these are two different crystallographic directions. This is what does it mean, a crystallographic direction or orientation. That these atoms are arranged, are oriented in this direction, but these atoms are oriented differently. So this is a difference. This makes this group of atoms form a crystal, which would be counted as another crystal than when compared to this group of atoms. So this group of atoms form another crystal, another grain. But you should understand, here when we mention another crystal, this doesn't mean that they do have two different crystal structure. No, they do have the same crystal structure, but oriented differently. So that's why it is better if we say that these are two different grains of the same crystal structure. This is one grain, and this is another grain. So that's why basically when we talk about polycrystalline material, we are describing these crystals are grains, not crystals. They are still crystal, the same crystal structure. But it is better if we can call them grains, but you should understand that the grain is still a crystal, but of two different orientations. The same thing, if we're gonna observe this group of atoms that located inside here, in between, they do have a different crystallographic orientation, right? All the atoms are arranged in a different way, in this way. Someone could say, okay, why did you choose this vertical plane? Can we choose this horizontal place? Yes, you can. You can have also you're still having a different crystallographic orientation. Like if we choose these horizontal ones, so we have to do the same here, right? For the other. So as you can see, the vertical and horizontal planes, they are oriented. This gives like a net that is oriented differently than the other net, and the same thing here. This net is totally different. It is oriented in a different way. So this known as misorientation. Misorientation. What does it mean, misorientation? It is a difference in the orientation from one grain to the other grain, from one group of atoms to another group of atoms. So this will form a virtual boundary between them. Virtual, what does it mean? It means that there is no specific boundary that is physically exists, but this boundary will show up, will be seen as dark line. This dark line, this is a boundary. This is another boundary of the same grain. These are the boundaries of this grain. And this is another boundary of this little small grain and boundary and so on. So all of these dark lines, these indicate a boundary. This boundary has been generated because of what? Because of the difference in the orientation from one grain to the other grain. But if you do have two grains, they do have the same orientation. In many of the cases, these two grains will be counted or considered as one single grain. And in many of the cases, there is no boundary that is going to generate between them. But this boundary shows up under the condition that there is misorientation between one grain and another grain, or group of atom and another group of atom. So this group of atom will form one grain, this group of atom form another grain, and there should be a boundary that is going to show up between them. This boundary, it is virtual. This line, it will be seen in the TM, yes, but this boundary indicates there is nothing there. There is no atom, there is nothing within this region that indicates that this is an empty space between one grain and another grain. Why? Because of the misorientation, because of the difference in the orientation. So this form a grain boundary. So simply, a grain boundary, it separates two grains or crystals having two different crystallographic orientations in a polycrystalline material. This grain boundary could be low or a small angle grain boundary, or it could be a high angle grain boundary. So we do have low angle grain boundary. We could name it as small angle grain boundary. We could have high angle grain boundary or large angle grain boundary, but it is commonly known as low angle grain boundary or high angle grain boundary. What is the difference? So these are like two states, not types of boundary. We can count them as two different types of boundaries of the grain boundary, but still they are grain boundary of two different cases or two different types. One is low angle, one is high angle. What is the difference? The difference depends on the difference in the misorientation, the angle of this misorientation. So that's why this angle is known as angle of misorientation or misalignment or misorientation. What does it mean? It means that as we agreed that this group of atom is aligned to form a crystallographic plane. This is the plane of atom in this direction, while this one has another direction, right? So there is an angle between them. They're gonna form an angle. If we measure this angle, this indicates how these two grains are misoriented to each other or misaligned to each other. So this boundary will be counted, whatever it is, low angle grain boundary or high angle grain boundary, based on this angle. So for example, this angle is given by a certain value if you're gonna compare the misorientation between this grain and the same grain over this boundary. So there is another boundary. This boundary is different than this boundary, right? Over this boundary, the misorientation is a very small angle. So the angle of misorientation here, it is smaller for this grain boundary than this grain boundary. The angle here is bigger. This indicates that this grain boundary, it is a high angle grain boundary, but this one will be counted as a small angle grain boundary when you compare this one to that one. If there is, the question is, if there is a specific angle based on which we can say that this is small, low angle grain boundary or high angle grain boundary, there is no specific angle, but this depends on the application, depends on the material type, depends on the comparison between one grain boundary to the other one. So for example, if we're gonna compare this grain boundary to this one, no, this one it will be counted as a small grain boundary, but this one is a high grain boundary. Angle grain boundary. Make sense? So the low angle grain boundary is a grain boundary that separates grains with a small degree of misorientation, but the high angle grain boundary is the grain boundary that separates grains with high degree of misorientation, as explained here. So again, the grain boundary, this is the second type of interfacial defect that would be exist in a material. Grain boundaries also could be in, so these are like two states as I mentioned. But also grain boundaries could be like tiled grain boundary. These like types also of grain boundary or twist grain boundary. Like as I mentioned, the grain boundary, it generates because of misorientation. There is also another way that could represent or result in the formation of a grain boundary within even the same crystal or even within the same grain. Like for example, if you have a single crystal, a single grain, and for some reason, there are some dislocations. We discussed the dislocation that we do have edge dislocation or screw dislocation. So if we assume that you do have one crystal, and for some reason you squeezed one half plane. So this is a dislocation, and this is the dislocation line that indicates that this plane, it is a dislocation. It is dislocated plane. And for some reason, there is another dislocated plane. And for some reason, there is another third dislocation plane, and so on. It means that you have multiple edge dislocations. And as you can see, all of these edge dislocations are somehow aligned over the same line. And they do have the same sign. Same sign means that same direction. That the compression above and the tension will be below this dislocation line. Make sense? So they are having the same sign, the same direction, and they are aligned over one line. This will form a special type of a grain boundary is known as tiled grain boundary. So again, the grain boundaries in general, whatever it is, tiled or twisted grain boundary or the normal grain boundary that shows up of misorientation. So we were discussing here the grain boundary that would show up because of misorientation between two different grains. This is one form, one way of forming a grain boundary, that it could be low angle grain boundary or high angle grain boundary. There is another way of forming a grain boundary, that the grain boundary for the same crystal, the same grain, could be formed because of multiple edge dislocations which are aligned of the same aligned over the same line. This is gonna form a virtual grain boundary that indicates the difference in the orientation between one part and another part. Going back again to the definition of the interfacial, we said that the interfacial defect is something that separates two regions, two parts of the same grain or two different grains. So if they are two different grains, no problem, we can have one orientation, another orientation. This is the grain boundary in general that distinguish one orientation from another orientation or one grain from another grain. Can we have a grain boundary within that is going to form within the same single grain? Yes. And in that case, we're going to deal with it like two grains after the formation of this boundary. So, like in the case that you have edge dislocation, this group of edge dislocations are aligned vertical over the same line of the same sign, so they're gonna form a virtual boundary that it would be located here, separating this part from this part. This part of the same grain from that part of the same grain. Why? Because the orientation of the planes will be oriented right, but the planes here will be oriented left. So there will be a misorientation. So that's why a grain boundary should be given here, or it will generate here. So the tiled grain boundary is a low angle grain boundary. What does it mean low angle? Because the misorientation between this side and this side in many of the cases is going to be low angle. There is no big difference in the misorientation between this one and this one, because originally they were completely parallel. When we added the dislocation one by one, this will result in this side is going to rotate and this side is going to rotate. So we're going to have a misorientation, but the angle of the misorientation will be too small. So that's why it is counted as low angle grain boundary, which is formed when multiple edge dislocations of the same sign are aligned together in one boundary, over one line to form one boundary. So this is going to make either the same grain, this is one side and this is the other side of the grain, that you're gonna find like they are like, instead of having like one single grain, they're gonna have like two separate parts. So there will be an angle between them, and this angle will be the angle of the tiled grain boundary, of misorientation of the tiled grain boundary. Also, we do have twist grain boundary, which generates in case that would have multiple screw dislocations, not edge dislocations. So if we have multiple edge dislocations within one grain, this would result in the tiled grain boundary, which is still low angle grain boundary. The twist grain boundary is an array of screw dislocation, not edge dislocations, aligned to give a boundary with an angle of misorientation that is parallel to the boundary itself. In this case, the two grains or the two parts of the crystal would seem typically the same, like the Rubik's Cube. We discussed that the screw dislocation, it is just a shift of one part of the crystal with respect to the other one. This is if we just added one screw dislocation. How about if we added more? So you're gonna give more shift, added more shift, more shift. This would result in one part will be completely twisted. When we compared the screw dislocation with the Rubik's Cube here, we said that the Rubik's Cube rotates about the center point. But the screw dislocation is a little bit different. It is similar concept but different thing. Why? Because in the screw dislocation, we're just shifting one part with respect to the other part. But there is no complete rotation. There is no complete rotation between one part and the other part. It's just shifting one lattice, two lattice, and so on. But in the edge, in the twist dislocation grain boundary, in the twisted grain boundary, what is happening? If you added more dislocations, you're gonna make the upper part will be completely separate. But in the one, if you just added one screw dislocation, the upper part is not completely separate. It is still connected. As you can see, it is still connected from behind. It is only one portion has been shifted right or left. So it is not a complete separation of the grain. It is still one grain, it is still one crystal, but there is a defect within this crystal as a screw dislocation. But if we added more screw dislocations, this could result in a case that you're going to have the top part completely separate and is going to be completely rotated like the Rubik's Cube, like this layer of the Rubik's Cube is going to completely rotate. This will result in another defect. So we do have two combined defects here. We do have a screw dislocation, that multiple screw dislocation that would result in one plane will be one half of the, or one part of the crystal or the grain will be completely separate from the other one, which would be typically the same like the Rubik's Cube. And in that case, we're going to say that we do have a twist grain boundary that is going to generate between these two bars to represent the misorientation that is happening in these two parts up on these screw dislocations. So it is an array of screw dislocations aligned together to form. Also, they should be of the same sign to give the same orientation, with an angle to give a boundary, with an angle of misorientation that is parallel to the boundary itself. So the angle of misorientation, it is parallel to the angle to the boundary. So this red thing, this is the boundary. And here, but the angle of misorientation here, it is perpendicular to the boundary. So this highlighted red part, this is the boundary. The angle of misorientation for the tile grain boundary is perpendicular to the grain boundary, but here it is parallel to the grain boundary, indicating this is a twist. So this is twist grain boundary that also could be generated as one type of the interfacial defects. So these are the grain boundaries. In general, they could be low grain boundary, high grain boundary. There are some special types of this grain boundary which are tiled grain boundary that generate because of edge dislocation, or it could be generated because of twist dislocation. Dislocations also in case that you have two separate grains of two different misorientations. So definitely there should be a grain boundary between them. Make sense? The last type of defect that we have here is the twin boundaries. Twin boundary is different than the grain boundary. Remember, the twin boundary is not a type of the grain boundaries. We said that we do have the interfacial defects, we do have external surfaces, and we discussed the external surface. So this is one type. Grain boundaries, they are another type. This grain boundary could be low angle grain boundary, high angle grain boundary in general, and there are some special types of this grain boundary, tile grain boundary, twist grain boundary. But the twin boundaries, they are not grain boundaries. This is another type of boundary, okay, which is similar to the grain boundary but is different. So the twin boundary, and we do have a stacking faults and phase boundaries, but we were not going to discuss these things because they are not included in the textbook. But anyway, the twin boundaries, which is this one, it is a special type of the grain boundary, but in many cases, as I mentioned, we are dealing with it like it is a different types of interfacial defect, that it could be different than the grain boundary, but it is a special type of the grain boundary. So it could be counted as a grain boundary, but as I said, it is a special type, or is a different type than the grain boundary. It will not be counted completely as a grain boundary. So it is a special type of the grain boundary across which there is a special mirror lattice symmetry, that is atoms of one side of the boundary are located in mirror image position of the atoms in another side. This is like in case that you do have like two twins, so that's why we are getting the twinning name, or the twin boundary. Twinning boundary, it means that you do have two grains, there is no misorientation between them. It means that this grain, the atoms are completely perfect, straight, vertical and horizontal. This grain, it is the same. So this is like one crystal, another crystal, one grain, another grain. But for some reason, these two grains, they have been welded or merged together in such a way that make one grain is oriented this way, and the other grain which has the same crystallographic orientation and the same crystal structure, but it had been rotated. So this would result in another way of misorientation between this one, and this would result in a grain boundary known as twin grain boundary or twin boundary or twin plane. So it is like a mirror. For example, if we assume that this plane is vertical, let us assume that this plane is vertical. So this would result in making this side, this atom, this group or crystal on the right, it should be rotated vertical. Both to make this twin boundary to be vertical. If it is vertical, so these two grains will be completely vertical and they're gonna have the same typical crystal structure with the same orientation. So they will not be counted like two separate grains or two separate crystals. And instead, we're gonna deal with them like they are one single grain or crystal. But since this plane is aligned, this is gonna result in a misorientation between this grain and this grain. But in case that this plane is vertical, there is no misorientation will be there, and these two grains like kind of merged and welded together, this is gonna form a twin boundary. That this boundary mainly generated under special condition, that the material it should be severely deformed, and this would result, as I mentioned, in one grain will penetrate into the other grain to form this twinning. But the twinning boundary, it will not show up like the other grain boundaries. Grain boundaries could show up because of dislocation, or it could show up because of misorientation nature of this material, like one grain oriented differently than the other one, and you still have one grain is separate than the other one. Two separate grains. But for example, if one grain have been penetrated into the second grain, this will result into another boundary known as the twin boundary. Okay, so that's why it could be considered as a different thing or another group than the grain boundary, the conventional grain boundary. So it is a special type of the grain boundary which is mainly generated to represent like there is a symmetry. This is like a mirror over around this plane, that you still have the same crystal structure within the same crystal or two different crystals, they have been welded or merged or penetrating to each other to form or generate this twin plane. Twinning produces due to annealing or some mechanical deformation, and this will be discussed in details in the next chapter, especially chapter 7, I believe, when we discuss the strengthening mechanism, and we are going to discuss how this twinning is generated. Twinning, it means that the generation of twin boundaries. So the twin boundary, it represents a specific mirror lattice symmetry around it, where atoms on one side of the boundary are located in a mirror image positions of the atoms of the other boundary. And as I said, this requires a special formation, or to form this twinning require annealing or severe plastic deformation, so we can form this twinning. Make sense? So that's it for this chapter 4. The objective again is just to discuss the different defects that would be located inside the material microstructure, and we have discussed these different defects based on the atomic structure. Like we have some of these defects are point defects, some of them are line defects, some of them are interfacial defects that related to group of atoms or plane of atoms that had been defected. So these imperfections are very important to understand them and understand the difference between them. Again, why? Because we are going to use them over the next chapters when we try to connect these defects to the material properties, and this will be discussed in details over the next chapters, especially chapter 7 as I mentioned. Okay, so that's it for today, and thank you, and see you in the next video.